So if you look at this example here, we got electron donating groups, and electron withdrawing groups. And then the reaction condition is nitric acid, sulfuric acid mixed together, so that's nitrogen. If you look at the electron donating groups, that's ortho parallel. So it wants to put here, there, right? If you look at the preference given by the nitro group, which is electron withdrawing groups, that's a meta electrons. So meta position to that is this one and that one. But that one's occupied, so probably we're going to think about this position. And that position is between the two substituents, so probably not going to think about that positions. So it's either this position or that or this one. So they are not in agreement anymore. Then which position will get the substitutions, right? So for that, I want to ask you to remember that electron donating groups stabilize intermediate, make the reaction go faster. Electron withdrawing groups destabilize it, make the reaction go slower. So which one has a louder voice? The one that makes it more stable, right? Rather than the one that makes it destabilizing. So electron donating groups, which is activator, usually listen to the voice of the electron donating groups, activators, instead of the electron withdrawing groups, deactivators. So these methyl groups is an activators, which can stabilize it. So that's where we think the preference is going to be dominated by, not the one that destabilizing intermediates. So be either here, there. Because of this molecule is not symmetrical anymore, we're going to have a mixture. One, nitro groups introduce that positions. Two, nitro groups introduce the other positions. I don't expect too much differences between these two, so we will probably get just 1-to-1 mixture. But it will be those two, not the one meta to nitro. Because that is not what stabilizes intermediates. Nitro makes it destabilizing, so you shouldn't listen to a voice that makes things worse. You should listen to a voice that makes things go better. So that is the first thing I want you to remember. Now, look at this molecule. Then you're going to find out we have methyl groups, we have amino groups. Methyl is a sigma donor, it's activated. Amino is also activators, but it's a pi donor, right? So if you look at the methyl groups, the methyl is an activator, it's an ortho paradirectors, which is an ortho position and para position. That's the where it wants to put the electron bonds. And that is blocked because we already have amino signal in that position, so we should consider that. If you look at the amino groups, amino is also activators and it's also paradirectors. So also position, para position to the amino is different positions. So both are activators, and then they want to put in different positions. Then where is going to be substituted in the end? So that's the question. And some of you probably already get an idea that, reaction normally happens with the most stabilizing intermediates, right? We got activators stabilizing intermediates. We got another activators can stabilize intermediates. But the most stabilized one will be the one they follow, and then that will be the one use the product. So which ones are stabilizing intermediates more is basically asking which ones are stronger electron donating groups, or in a way that which ones are has a more powerful one. So that's why we talked about those chart. Electron donating groups, there's a difference in strength. Alkyl groups is not the stronger one, but a sigma donor. The amino groups, that has a low pair, that is a pi donor, that has a more stronger activators compared to alkyl groups. So when more strong activators and weaker activators, which one's going to be dominating? The most stronger one, right? So I'm pretty sure that this is a very reasonable guess of conclusions. one thing that I want to mention that this, when I wrote this one down, I forgot that this is actually the amino. I don't know why. You don't need a catalyst, right? Because aminos are already too powerful. If you just plug it there, you don't even need a catalyst. So you can simply just cross it out. But anyway, still the same thing. Is amino prefers this position also pair to the amino. Methyls are also paired to the methyl, but which one is going to substitute more? Probably the most stronger ones are directed one. So we think it's going to happen here and there. So just cross it out, not the ferric bromide. I mean, of course, this is not going to be this, but the amino basically electron density is coming in, that pops out, taking the bromide, and that's how it's happening. We're going to end up bromine in this position, which is also to that bromine is going to be para position to that. So that will happen. Right. So after we teach you this is probably what we're going to ask in the test. Many of you, I mean, you kind of tasted this a little bit in the last class, but many of you just saw that we got activators, two activators, and then aminos are most stronger one. That's the reason why it's happening in this position. That's why we get these two products. So if someone just memorize how to solve the question without thinking about it, then when we ask another question, same molecule, but this is nitration conditions. Then we saw it happen also para to the amino groups. So they should really just put the also para to that molecule. Then that is a wrong answer, right? So that's why just memorizing how to solve question is not a good idea. Probably not has been a good idea for the mathematics, and then it's not a good idea for the organic chemistry, because organic chemistry you should treat it like mathematics for the life sciences. So, but why this is not happening? Why the same conditions doesn't work here in this question? It is a nitric acid sulfuric acid mixture that is a very strong acidic reagent, and then amine is a base. So when acid meet with a base, they basically neutralize. When the proton was given to the amine, then it's going to be an ammonium group, right? When it becomes an ammonium group, this is not electron donating groups anymore, because it doesn't have a lone pair, and it's a permanently positive charge. That is a very strong electron withdrawing group. That is a metal. So now, most strong activators in this molecule turns to the most strong deactivators upon the protonations. So you got to look at the reaction condition carefully, especially the amine, because an amine is a base. If these are hydroxyl groups, I don't expect this happen because the hydroxyl groups are not that easily protonated. Hydroxyl groups are more like a neutral. I mean, of course, you can temporarily protonate it. That's how we do the dehydration of an alcohol, but not going to stay as a protonated in the majority of the time. So amine, however, is a base. It's going to be protonated. It's going to be existing like this almost like 100% of the time. But that's the difference between the hydroxyl groups and the amino groups. But once it becomes an ammonium groups, then now there's an activators, that's the deactivators, and then activators wants to put the also para positions, and that position happens to the mana position to the deactivators, so both in agreement. So when you do the nitration to that molecule, you're going to get the nitro goes here and there, also para to the messages. So not only the study material where you get the substituents, you really need to look at the conditions as well. But this is the kind of the things I want to mention that we really want to work it out.